So last week we talked a lot about matrix vector multiplication, and we defined what a matrix vector multiplication is. What I'd like to do next is talk about algorithms for computing matrix vector multiplication. Let's start by looking at an algorithm for matrix vector multiplication that uses the dot product. So here we have a vector y, and we're multiplying a times x in order to compute it. Notice that the number of rows in A must be the same as the number of elements in Y. The number of columns of A must be the same as the number of elements in X. And when you do the matrix vector multiplication, compute the first component of Y, you multiply this times that plus this times that plus this times that. To compute the second component, you do this times that plus this times that plus this times that, etc. So notice that the components are coming out right here. If you look at a typical row in this result vector right here, what you notice is that that's just a dot product of this row of the matrix A with the vector x. That's stated right here. So to compute components of y, all one has to do is do a dot product of the corresponding row of A with the vector x. This explains a little bit the notation x transpose y that we saw before. If we did x transpose y, notice that transposing this vector, which we can also think of as a matrix with only one column, gives us a row vector, or a matrix with only one row. Now, if we think of this as a matrix vector multiply, where this is your matrix A and that is your vector x, notice that A only has one row, so the result vector only has one element. And notice that you compute this by doing this times that plus this times that plus this times that. Let's do an example of a matrix vector multiplication. Notice that here we need to do dot products of the rows with the vector. So the first result vector is minus 1, 0, 2 times minus 1, 2, 1. That's a dot product. The second element of the result vector is 2, minus 1, 1, dot product with minus 1, 2, 1. And the last component is 3, 1, minus 1, dot product with minus 1, 2, 1. Okay, and then you can work this out, what it exactly is. Let's see. This is minus 1 times minus 1 is 1, plus 0 times 2 plus 2, so this is 4. This is minus 2 plus 2 is 0 plus 1 is 1. And then 3 times minus 1 plus 1 times 2 is minus 1. Minus 1, I think that's minus 2. So the result vector should be 4, 1, minus 2. Now let's look at an algorithm for computing y equals 8 times x. Well, what we're actually going to do is something slightly different. We have vector y, we have matrix A, and we have vector x. And what we're actually doing is we're adding the result of doing the matrix times the vector multiply to the vector y. Now the reason for that is that the algorithm is going to be a little bit cleaner. So let's have a look. Here's the algorithm. Now what's going on? Well, this is the general algorithm. So we put in general row and column size for the matrix and the vectors. So here, this is m, this is n. And what we're going to do is we're going to use an index I to indicate where in the vector here we are. And then we're going to use index j to indicate where in our dot product we are. So let's fix our I to be one of these. Let's say 2. Then if you look now at this inner loop here, What's it doing? It goes from 0 to n minus 1, so it goes in that direction right there. And what it does is it takes this element times that happens when j is equal to 0, plus this times that, plus this times that, except that we're accumulating into psi sub 2. Okay, we're accumulating. We're adding to that vector. So this is known as a doubly nested loop, and the outer loop simply runs down the elements of y and therefore down the rows of A, and the second index j then goes across the columns of A and down the components of x. Now let's look at this a little bit differently. Notice that we just talked about the fact that we can think of the individual elements of y being computed as dot products of rows of A with the vector x, except we're accumulating, we're adding to. What we could do is we could simply create a symbol that denotes this entire row. How do we do that? Well, here we take this entire row, and we notice that it's a row vector. So we're going to call it a tilde 0. The tilde comes from the fact that sometimes it'll be a column, sometimes it'll be a row. If you want to explicitly make it clear that it's a row, I'm going to put that tilde on it. And what we're doing here is we're saying, well, it's a vector, except it's a vector turned on its side because it's a row vector. So the symbol I'm going to use to denote that row is a sub 0 tilde transpose. Transpose is because it's a row vector. And I can do the same thing for the second row, the third row, and the fourth row, creating symbols for those rows. Now notice that all we need to do is take dot products of these rows with vector x. Okay, and that we can indicate like that. And this makes it very, very clear that we're updating the components of y by adding the results of dot products to it. We can use this to explain our doubly nested loop slightly differently. It's still the case that I goes down the components of y and the rows of A. But what we can notice is that this second loop here was simply doing the inner products accumulating into the appropriate component of y. What we can do is we can say, look, all we're doing is take the ith row of A, do a dot product of it with vector x, and add that to the appropriate component of y, overwriting that component of y. So now we actually have one loop and a dot product. And notice that this here we could actually implement as a call to our routine laugh.dot. We could also express it using this flame notation that we've been using so far in the course. And since we have a programming assignment associated with this, I'll just let that programming assignment make it clear what's going on here. So in summary, a matrix vector multiplication you can think of as taking dot products or inner products of the appropriate rows of the matrix with the vector being multiplied. What's important here is to notice that matrix vector multiply can now be described in terms of dot products. Okay. Similarly, you're going to see in the programming assignment that a matrix vector multiply routine can be implemented in terms of a dot product routine. So, the layering is starting to become obvious both on the math side and on the software side.